In Chapter 8, we'll be expanding on our reactions of alkenes and alkynes. The enzyme that we're looking at here is called enoyl-CoA hydratase, and this is going to catalyze the reaction of adding water across a double bond, and this occurs during fatty acid metabolism. At the beginning of Chapter 7, we saw the formation of enoyl-CoA with that double bond there, and now once we form the double bond, we can add water across the double bond. And there's a lot of different reactions that we can do once we have an alkene that's formed. So it's going to react with a lot of electrophiles to give us a whole bunch of different functional groups. So we can see alcohols, alkanes, carbonyl compounds, epoxides, alkyl halides, etc. One of the reactions we can do is a substitution reaction, where our Br is going to be replaced with the OH here. This can also be called the functional group transformation. So here's the OH that's added. We have a Br minus here. We can also do an elimination, where this gets eliminated and replaced with a double bond. And that requires something that's going to act as a base. We form water in the process as well as Br minus. So these alkyl halides that we have here can react with a nucleophile or a base in order to form the substitution reaction in the case of a nucleophile, or an elimination in the situation of the base. Some of the reactions that we can use in order to make an alkene is to do a dehydration or removal of water, and that involves an alcohol plus acid. So we're using sulfuric acid as our acid, and we're going to heat that up with water. This is my carbon skeleton. So what we're doing is taking the hydrogen that's adjacent to the alcohol. We're going to remove that as water and form a double bond in the process. The THF is a solvent, which is shown below there. That's just a cyclic ether. And it looks like we have the same reaction twice. This is going to be my major product. And we have another hydrogen that's possible here that can get eliminated. This will be the minor product. What we want is the most substituted alkene, because that one's the most stable one. So in this first alkene, we created a tri-substituted alkene. So there's 1, 2, 3 groups coming off of that alkene. This one is only di-substituted. So that one is less stable, so that's why that one is the minor product. So that's one way of forming an alkene. Once we have the alkene, we can do several reactions with them. One of them is going to be a halogenation reaction. This falls into the functional group transformation category. And we have cis-2-butene. We're going to add chlorine across from it. And the way that chlorine is going to add is trans to each other. So one chlorine is going to be wedged, the other one is dashed. So we're going to get a trans product. Bromine is going to do the same reaction. We're going to add 2 Brs across the double bond, and they will be trans to each other. So bromine and chlorine are going to add to give 1,2-dihalides, which is a very important process industrially. Fluorine does not react. Fluorine is too reactive, so we don't generally use fluorine in these reactions. And iodine does not happen because it's too slow. So chlorine reacts as a Cl plus and a Cl minus. It kind of polarizes itself to react, and Br does the same thing. If we do a reaction with cyclopentene, the process here is the same. We're going to add Br2 across the double bond, and they're going to add trans to each other. So we'll get this Br where it's wedged, this one's dashed. And usually you get the enantiomer as well. In this case, it happens to be the same thing, but you can get this product as well as the other one. So we're going to form the trans 1,2-dibromocyclopentane. And what happens is one Br is going to add. It's going to form a cyclic structure. And the other Br that's present is going to do a nucleophilic attack here on the backside. So if these were wedged, that's going to attack from the backside and open up your bond here in order to form the trans product. So addition is exclusively trans. And this structure here is called a bromonium ion. Halohydrins can form from alkenes. So a halohydrin has a halogen, and the hydrin is the water part of it. So in this reaction, we're going to add one halogen and one water, and we're going to form the halohydrin. So one of the carbons of the double bond is going to get the halogen. The other one will get the alcohol. This is a halohydrin. We also form HX in the process. So again, we're going to form a bromonium or a halonium. And the water is going to do a nucleophilic attack on one of these sides here. That will open up, and then we form our halohydrin. In the formation of a halohydrin, there's a couple of things to consider. The addition, if I'm going to adjust this here, these are added anti to each other. So this will become wedged, and this one will become dashed. So X and then the OH add anti. And the second thing to remember is that if you have an asymmetric alkene, the OH is going to go to the more substituted carbon. So for example, if I had this methyl cyclohexene, and let's say I add Br2 in water, the Br is going to add to the less substituted carbon, which is this one right here. And let's say this one is wedged. And then my OH is going to be anti to that, and it's going to be on the more substituted carbon. So this will become wedged. We can hydrate an alkene. This is just the addition of water, and we get an alcohol in the process. So when doing hydration reactions industrially, we have to use an acid catalyst as well as high temperatures in order to convert ethylene to ethanol. So we have ethene or ethylene. Here's our carbon skeleton. So we add an alcohol to give ethanol. If you wanted to draw the hydrogen in, you certainly could there. So in this reaction, the process works fine, but if you have more substituted alkenes, it could result in a rearrangement. In an oxymercuration reaction, we're going to add water across the double bond to give us an alcohol. This is a Markovnikov product. There's no rearrangements possible. And remember that a Markovnikov reaction is where the OH is going to go to the more substituted side of the alkene. If we're going to look at our alkene, the more substituted side is the one that has more carbon groups coming off of it. So that's where our alcohol is going to go. We don't have to worry about rearrangement. So my OH goes to the more substituted side. The hydrogen, if you choose to draw it in, goes to the carbon that has more hydrogens. In a hydroboration reaction, this is addition of water again. We also get an alcohol here, but this is an anti-Markovnikov reaction, and we still have no rearrangements here. And in the case of an anti-Markovnikov reaction, our alcohol is actually going to go to the less substituted side. So this is our less substituted side, and that's where our alcohol will go. So there's my carbon skeleton. My OH goes to the less substituted side, and this usually results in a syn addition. So my hydrogen gets added here, which makes my carbon here dashed. So here are the different ways of hydrating an alkene or adding water across the double bond. The alkene reacts with the acid. It then forms a carbocation. So what I have here is a secondary carbocation, and I have a hydrogen next door that can shift over. And when it does that, it forms a tertiary carbocation, which is more stable. And that's where the OH is going to form. So if you're trying to make an alcohol, and there's a potential for a rearrangement, it's likely to happen. So if you want to avoid rearrangement, you want to use the oxymercuration. So this is going to give us a Markovnikov product with no rearrangement. So my carbon skeleton will stay the same, and my OH is going to add to the more substituted carbon, which is this one right here. So I get an OH here. Drawing in the hydrogen is optional. And then this BH3 reaction is going to give us an alcohol at the anti-Markovnikov position, and we'll have no rearrangement here either. So it's going to add to the end carbon. H and the OH add to the same side. You don't need to draw in the hydrogen if you don't want to. So you can do a couple of practice problems here with these. An alkene with Br2, my skeleton is the same. I'm going to add 2 Brs across the double bond. You can think of it like this. They're going to be trans to each other. So we have this Br. Technically, if this Br is wedged, that's going to push one of these into the dashed position, so you can adjust there if you need to. For a chlorine plus water, we're going to form a halohydrin. The water is going to go to the more substituted position. These also add trans to each other. And then now, if we think backwards a little bit, we have an alcohol that's added to the end using the hydroboration reagents. We want to think about what alkene came first. My carbon skeleton is going to be the same. I just need to think about where my double bond was. And if it's coming off the bond here, we really only have one place for that to go, and that is here. Another reaction that we can do, this is going to be the first of our reactions to add to reduction reactions. And a reduction, if you recall, is gain of something. And here we're going to gain hydrogen. In this reaction, we have hydrogen, which is in pink there, that H2. This is usually accompanied by a metal catalyst, in this case platinum oxide. And all it does is add H2 across the double bond, which you can draw in or you don't have to. And these add syn to each other. So this is a syn addition. So we're going to add H and H across the double bond. You don't have to draw the H's in, but I'm just showing them so you see what the reaction is. So what happens is that the hydrogen is going to attach to the metal surface. On the same side of that metal surface, the alkene comes in here, lowers itself down, and the hydrogens are going to add to the same side. So we get this syn addition of the hydrogen. This is going to require a catalyst, which is going to be platinum or palladium. It can also be a nickel catalyst. So hydrogen does reduce a lot of things, and this can be an explosive reaction because hydrogen, as we know, is flammable if you're not careful. It will reduce dienes. If we have 2 double bonds, that's going to reduce the double bonds, so that we just have cyclohexane here from cyclohexadiene. It will reduce the double bond here in this ester, but does not reduce the benzene double bonds. And then if we have a nitrile, the C triple bond N and this alkene here, that's going to reduce only the alkene. So it's going to leave the nitrile alone. We can reduce polyunsaturated fats. So you may have heard of fats being partially hydrogenated. And in that process, we take something like vegetable oil, which is a polyunsaturated fat, which means it has many double bonds. This is liquid at room temperature. And then if we take some of those double bonds, there happen to be cis double bonds, we're going to reduce those into something like margarine. So now we've added these hydrogens across here. And margarine, as you know, is solid, and it's a spreadable solid. So we take vegetable oil and reduce some of the double bonds by adding hydrogen, and that turns it into a saturated fatty acid, which is solid. And sometimes in the process, when you're doing this, this can create trans fatty acids, which are not good for us. Okay, so in this problem, we're going to figure out what products are expected when we do a hydrogenation of these alkenes using H2 over platinum. And we're just going to add hydrogens. So here there are H, H, or you can just draw it this way because we don't need to draw in hydrogens on carbon. And then for this cyclopentene here, if I'm not drawing in my hydrogens, that's my product. We can do oxidations of alkenes now that we've done reductions. The oxidation, remember, is loss of H2 or gain in CO bonds. One of these reactions involves an alkene and something called metachloroperoxybenzoic acid, which we can abbreviate MCPBA for metachlorobenzoic acid. And what that is going to form is an epoxide, which is a 3-membered ring with oxygen in it. We also get the metachlorobenzoic acid as a side product. So epoxidation results in a cyclic ether. And once you form an epoxide, these can undergo ring opening reactions. So the oxygen comes from this peroxybenzoic acid that forms this little 3-membered ring coming off of where the alkene was. We get benzoic acid as a side product. Once we form an epoxide using epoxidation, we know that these 3-membered rings have angle strain, which makes these excellent electrophiles. So if I add something like H3O+, which is the same as adding acid and water, that water can do a nucleophilic attack and then open up the epoxide to give us a trans diol. So hydroxylation is a 2-step reaction. This involves first protonation of the epoxide, and that comes from the acid part in the acid and water. And then we have water, which can do a backside nucleophilic attack on that epoxide that was protonated. And then we just have another proton transfer to pick up that extra hydrogen on the water. And that's how we get our trans diol. Benzoapyrene is a carcinogen that's found in cigarette smoke, soot, barbecued meat, and usually anything that involves burning. It's detoxified by converting it to a diol epoxide, which we can see right there. And then as that sits in our bodies, water is added, and also epoxide hydrolase enzyme can cleave that into this tetrol. Then the hydrolyzed tetrol is now water soluble, and that can be excreted in our urine. Hydroxylation of an alkene can happen also with osmium tetroxide, or OSO4. This is going to result in the syn diol, so the alcohols are on the same side. So we first form an osmium complex. And then the second step is to add the sodium bisulfite. That will cut off our osmium and leave us with these OHs. This reaction can also occur using NMO, which the structure is shown there, that N-methylmorpholine N oxide. Reaction is the same. We're only going to react across the double bond though, not on the benzene ring. And we add our alcohols syn to each other. We can take a look at a couple of reactions here. MCPBA by itself is going to form the epoxide. So that's that metachloropyroxybenzoic acid. So we get the epoxide. If we add acid and water to that MCPBA, we're going to form our transdiol. One OH is wedged, the other will be dashed. So the acid and water are going to open up that epoxide. And then if we do the reaction with cyclohexene with osmium tetroxide, that's going to give us a syndiol. So our alcohols will be on the same side as each other.